Section 3.4 is about concavity and the second derivative test. So basically we're diving more into what functions look like and how they behave at certain points and stuff like that. And so what we're in this section, we're looking at concavity. And what concavity is, all right, is whether it's concave up or concave down. The definition says let f be differentiable on the open interval. The graph is concave up if the derivative is increasing on an interval, and it's concave down if it's decreasing on an interval. And the easiest way for me to remember it is basically it's concave up if it can hold water. So from this interval to here, it's concave up because it can hold water, and it's concave down if it cannot hold water. I don't remember where I heard that. Maybe my high school math teacher, but that's the easiest way I remember what concavity is. We have a test to figure out whether it's concave up or concave down. It says let f be a function whose second derivative does exist. And we take the second derivative of it, we pick a point in an interval, and if it's greater than 0, then the second derivative is greater than 0, then it's going to be concave up. If it's less than 0, the second derivative is less than 0 at that point, it's going to be concave down. So what we have to do is we have to locate the x values of which the second derivative is 0 or it's undefined, much like when we're finding the critical points for finding the extrema. So here we go, example 1. Determine the open intervals for which the graph of f of x equals 6 times the quantity x squared plus 3 to the negative 1. Determine where it's concave up and concave down. So we need to find the second derivative, what we need to do. So let's find the first derivative. So the first derivative is going to be, looks like it's a chain rule. We have an inside and we have an outside. We're going to bring down my negative 1. So now I have negative 6 times, I'll leave my inside alone, x squared plus 3, and subtract my power by 1. And then I need to take that whole thing, since it's a chain rule, times the derivative of the inside, which is just 2x. So my first derivative is going to equal a negative 12x all over x squared plus 3 squared. So there's my first derivative. Now I need to find my second derivative. All right, so it looks like we're going to have to do the quotient rule here. The quotient rule says, let's do this. The quotient rule says that we bring up the bottom, x squared plus 3 squared, and take the times the derivative of the top, which is a negative 12, and then we subtract the top. So we subtract negative 12x times the derivative of the bottom. Sorry, I didn't mean to put that bracket there. So a negative 12x times the derivative of the bottom. So we're going to have to do the chain rule again. So we'll have 2 times x squared plus 3 to the first power times the derivative of the inside, which is times 2x. Like that. And then that's all over the denominator squared, x squared plus 3 to the fourth power. All right, so we have some simplifying to do. And let me clean this up a little bit. I'll move it a little to the left. So my f double prime, my second derivative is going to equal, let's make this a negative 12 times x squared plus 3 squared minus, it's actually going to be a plus because I have a minus times a minus, so plus. Let's see, I have a 12x, a 2, and a 2x, so I'm going to have 2 times 12 is 24, times 2 is 48, so 48 x squared, right, times x squared plus 3, all over x squared plus 3 to the fourth power. Looks like we have a common term up top. We have a negative 12 as a common term. We can take a negative 12 out, and we can also take an x squared plus 3 out. So let's take that out. So I'm going to take out a negative 12 and an x plus 3. And when I'm left over, then I'm left over with just one x squared. Sorry, this is squared. X squared plus 3, just left with one of those. And then I'm taking a negative 12 out, so I have a minus 4x squared. And I took this x squared plus 1, x squared plus 3 out, so it becomes a 1. All right. And I'm working on the top here. Let's just continue to simplify the top. I'll bring, well, let's put it in there. Let's put the bottom in there. All over x squared plus 3 to the 4th, which is nice because it looks like something's going to cancel out. Since we're multiplying here, we can cancel one of these out. This becomes a 3. And then if I combine terms in here, looks like I'm going to have a negative. This term inside here is going to be negative 3x squared plus 3. All right, so it looks like on this inside here, when it became this, looks like I can pull a negative 3 out. So I'm going to rewrite it, pulling a negative 3 out. So I'm going to have negative, actually a positive 36 times, and then when I pull that negative 3 out here, I get x squared minus 1 all over x squared plus 3 to the 3rd power. Not all second derivatives are going to be that complicated, but I wanted to show you a relatively difficult one just to freshen you up on your derivatives. All right. So now what we want to do is we want to figure out where the second derivative is going to be equal to 0 or when it's going to be undefined. So I'll set the top equal to 0. When we set the top equal to 0, all right, we'll set the top equal to 0. We divide by 36. I just have x squared minus 1 equals 0. We add 1 over. So I get x equals plus or minus 1, right? There would be when it equals 0. When the denominator is going to equal 0, looks like I can't really solve. It's going to be an imaginary number out of x squared plus 3 to the 3rd power equals 0. You know, take the cube root of both sides. You still have x squared plus 3 equals 0. You subtract 3 over x squared minus equals a negative 3. Take the square roots. They're imaginary numbers, so we're not going to have any real numbers that's going to make the denominator undefined, so we don't have to worry about that. So it looks like our really critical points for figuring out whether it's concave up or concave down or plus or minus 1. So I'm going to go from negative infinity to a negative 1 as my interval. And then I'm going to go from negative 1 to 0. And then I'm going to go from negative 1 to 1. And then I'm going to go from 1 to positive infinity. And we're going to pick values. We'll plug it in the second derivative. If it's going to be positive, it's going to be concave up. If it's going to be negative, it's concave down. All right, so let's pick a point inside here. So let's pick negative 3. When I pick negative 3, I'll have negative 3 squared, which is 9 minus, I'm going to have a positive on top. Again, really, it doesn't matter what the value is. I don't care what the value is. I know when I'm just figuring it out, I'm going to have a positive up on top. When I plug a negative 3 on the bottom, I'm going to have a positive on the bottom. So it's going to be concave up. Since we have a positive over a positive, we're going to be concave up. It's going to be a positive value. So let's pick a point between negative 1 and 1. Let's pick 0. If I pick 0, I'm going to have a negative up top. And I'm going to have when I plug 0, I'm going to have a positive on the bottom. So I have a negative over a positive, therefore it's negative. And what our test told us, then it's going to be concave down. All right. And then pick a point from 1 to infinity, and we'll pick 2. When I plug 2 into my second derivative, which is right here, when I plug 2 into my second derivative, I'm going to get 36 times 3, so that's going to be a positive value up top. I have a positive value in the bottom. It's a positive or positive, so this guy is going to be concave up. So there's a test for concavity right there. I'm going to come back in the next video and show you the second derivative tests and points of inflection. All right.